My name is Avatamsa Athirasala. I go by Avi. I'm in the BME PhD program at Oregon Health and Science University.
My name is Anthony Tahayuri. I have education in biological engineering from Oregon State University. Currently, I'm a research assistant in the Bertassoni lab at Oregon Health and Science University.
We call our team Microcosm because what we're trying to do is build like a microcosm of a tissue. My role in the team is to bring the biology angle to our creative solution we've come to.
I am an engineer in charge of designing and implementing all of the ideas that we have for creating 3D tissues in using our device.
I guess the main challenge has been that we weren't allowed back in the lab for a long time. And when we did go back into the lab, we had multiple commitments that we had been trailing behind on. So time was a real problem. Time in the lab to be able to develop our product or test our product has been a major challenge.
My favorite challenge that I always like to bring up is that while it might seem perfect in theory, in practice, it's a different beast. You can say, oh, this feature size of what is proposed by the printer manufacturer is 50 microns or something really small. In actuality, what you're going to get is going to be triple the size. When you're designing something and you think, oh, I'll push it really close to the theoretical max, you really have to kind of manually do the fudge factors. Specifically OHSU, they provide us a lot of regulatory help in so much as protecting the IP of our device, giving us a regulatory platform that we can rely on, just so that I'm an engineer, Avi's a scientist, we don't do much legal work. That has definitely been a help to just say, hey, focus on what you do best. Let our institution actually carry this load.
My mentor specifically, Luis Bertassoni, who is a part of our team, although he's a scientist, he's an inventor, he has many patents to his name, and he's always been looking towards coming up with creative solutions to engineering problems in the world. And he has always guided us towards how to think about things from a commercial angle. And I think these aspects have been really important to us.
Microcosm is a light platform that cures materials. The material that we're curing in this case is a hydrogel. A hydrogel being it's a liquid that once it turns into a hard material when it cures, is something suitable for cells to actually grow on and in. In our field of science, 2D technology is prevalent. It's everywhere. It's really easy to do. Everybody's characterized it really well. But the problem is that we're not sheets of paper. We're human beings. We're three-dimensional. The tissues that we're looking at, they're also not two-dimensional. They're three-dimensional. So by creating a system that we can test and analyze three-dimensional tissues, we're getting much, much closer to analyzing what tissues are like and what responses they'll have in a laboratory setting, as opposed to having to test it in an animal or in a patient directly. It gives us much, much more flexibility as to how we can test it before we actually bring it to the patient or bring it to later clinical trials.
Make a fake tissue that you can study, see how cells behave in a body, and that can be used to understand what changes when a disease happens, how cells would respond to drugs, and all of that. So basically, this is more a model of your tissue that is in your lab that you can study. What's innovative about this is that we're using existing simple technologies like 3D printing that's been used to solve other engineering problems, and we are using that to solve our problem, where you have a high resolution, high precision associated with 3D printing. And we are able to use that to make really micro scale tissue models with high resolution that 3D printing is known for. We're a small lab, we're relatively new. We don't have like a ton of funding, but we have a lot of ideas. And our whole goal in our lab has been to use our innovative skills rather than a lot of money to solve problems. And so we've always been good at coming up with like hacky solutions, use something that's more off the shelf rather than a custom made equipment to solve a problem that we have in the lab. And I think that's one of the things, one of the reasons we came up with this as well. Like we were able to we found that we were able to achieve really high resolution micropatterning with the printer that we had, and we were able to use that to make tiny microscale tissue models.
The main goal is to add this extra complexity of the third dimension, but to also shrink down our testing environment. For example, a traditional test might be the size of a penny, and it might be in that 2 dimensions. With our size is about the thickness of a human hair, and we have many, many tests of it. So within that size of a penny, we're actually running about 50 different replicates. So we have 50 tests as opposed to the 1 test. If we're able to test the same thing 50 times, with our system, we're actually able to test 50 different things in the size of that 1 penny. If we can test 50 different things, that speeds up how many things we can test, and it can move forward with, say we have a drug, and we can test it 50 different times as opposed to 1 time in the equivalent testing space.